So after our graphical exposition, in which we decompose the total effect into a substitution effect and an income effect, we're now going to take a more mathematical approach. And first we will consider a discrete change in the price of the good that we consider. And to find the substitution effect, well, we want to tie the individual to the original utility level, to the original indifference curve. So the appropriate concept to use here is the expenditure function, because the expenditure function gives us how much we need to spend given the prices of the good and, importantly, given the utility level that we want to obtain. So the expenditure function gives us a relation between the demand for a good and its price, keeping the price of the other goods and the utility level constant. And that relation is represented by the compensated demand function, the Hicksian demand function. So this one is familiar. So the demand for a good X is dependent on the price of good X, the price of the other good, good Y, and the utility level that we want to attain. So, and if we keep this one fixed, then we will remain on the same indifference curve. And if we then study a change in the price of good X, what we will get is a change in demand that is the effect of the substitution effect. So let's do that. So here on the left hand side we again have the indifference curve U1, and suppose that we start out with a price px2, and again this is not a power but this is just an index, and at that price level our optimal consumption of good X is equal to x2, and that gives us also a point in the demand function of good X. Given that the price is px2, our optimal demand is equal to x2 units. So now we are going to derive the compensated demand curve, and we're going to sketch the relation between how we move along the indifference curve, staying on the same initial indifference curve U1, and how that will lead to changes in the compensated demand. So suppose that compared to the original price px2, the price decreases to px3, then the substitution effect is that we want to remain on the initial indifference curve, but we adjust our consumption such that the marginal rate of substitution is equal to the new price ratio of the two goods. So we are at the point of this original indifference curve that is tangent to the ratio between the new price of good X and the price of good Y. And then we get the compensated demand given price equal to px3, and on the right curve, on the demand function, we depict it as the point x3c, where the c is for compensated. So, and if instead we would have an increase in the price of good X, but we would compensate the individual such that he would still be able to attain his original indifference curve, then we again choose the consumption bundle that is on the old indifference curve and where the indifference curve is tangent to the new price ratio. Now this one has become steeper because px has increased, py has remained the same, so this ratio, the slope of the budget constraint, has become steeper, and this new optimal point is denoted by this point over here. So in the right curve, in the compensated demand curve, we have a third point related to if the price of good X is equal to P1, then the optimal consumption, if we get compensated, if we remain on the old indifference curve, is equal to X1. At this point you may wonder, how does the compensated demand curve relate to the uncompensated demand curve? And given that we have the uncompensated demand curve, why do we need the compensated demand curve in the first place? I will now show you the relation between the two, and that will also show you the additional benefits of sometimes focusing on the compensated demand curve. And it will turn out that in welfare analysis, the compensated demand function is very relevant. So suppose now that we have an initial price level Px2, price of good X, and that the consumer has an initial income equal to capital I. And this income level is just sufficient for this consumer to attain a utility level U bar. Now, under those assumptions, it automatically follows that the compensated demand function is equal to the uncompensated demand curve. So they are exactly at the same consumption bundle. So given that I want to obtain a utility level U bar and I face prices Px and Py, I minimize my expenditures by buying XC units of good X. And given that my income is I, and that's just sufficient to reach this utility level U bar, but no higher utility level, and given the same prices Px and Py, I will maximize my utility by spending such an amount on good X that I can buy X units of good X. So this holds by definition. And now we want to know how we will move along the uncompensated demand curve and the compensated demand curve if we increase the price of good X. Now, if we increase the price of good X, then one effect is the substitution effect. So we will substitute away from consuming good X, and instead we will start consuming more of good Y. That leads to a decrease in demand, and the compensated demand curve focuses on this substitution effect. It doesn't take into account the second impact of the increase of the price of good X, being the income effect. So the compensated demand curve will show you the decrease in the demand for good X as a result of the substitution effect. In addition, the demand for good X will decrease even further because an increase in the price for good X will reduce the income of the individual and the individual's purchasing power. And this income effect will lead to an additional decrease in the consumption of good X. So the Marshallian demand is below the Hicksian demand if the price increases. If instead the price of good X decreases, then again we will substitute away from the good that has become relatively more expensive. Well, if the price of good X decreases, it means that good Y has become relatively more expensive, so the consumer will buy more units of good X, and that's shown here at the compensated demand function. But in addition, there's also an income effect. Because good X has become cheaper, the income, the real income, the purchasing power of the individual has increased, leading to a positive income effect. So that will lead to an additional increase in consumption of good X. And given that the Marshallian demand function gives you the sum of the positive substitution effect and the positive income effect, the Marshallian demand function will be to the right of the Hicksian demand function. And that makes clear that the compensated demand function will be steeper than the uncompensated demand function. Another way to show it is as follows. So suppose that the initial price is Px2. Given our initial budget constraint and and that we maximize our utility, we can attain utility level U1 by consuming the bundle that gives us X2 units of good X. Now we decrease the price of good X, meaning that the marginal rate of substitution of good X and Y will change. And the substitution effect is that we adjust for this change in price ratio, but we tie the individual to the initial utility level, so the initial indifference curve. That's a substitution effect, and only the substitution effect will lead the individual to increase its consumption of good X from X2 units to X3. And that is the compensated demand. So given that we decrease the price of good X, the substitution effect leads us to increase consumption from X2 to X3 compensated. However, we also not only have a change in the marginal rate of substitution, but also we have a pivoting outward of our budget constraint. So our budget constraint is no longer this line over here, but the new budget constraint is depicted by this line over here. So it pivots outward. So, and we not only have a substitution effect, but on top of that, we also have an income effect that allows us to increase our consumption of good X even further from X3 compensated to X3. And we can also depict it in the graph to the right. So the total effect of the price decrease of good X is a substitution effect and an income effect. And the total effect is given as a point on our uncompensated demand function. So this also explains why if we decrease prices, the uncompensated demand function is to the right of the compensated demand function, and if we increase price of good X, then the uncompensated demand function is to the left of the compensated demand function. Okay, so we can use the compensated demand function to determine the substitution effect. And let's do one numerical example. Suppose now that the price of good X decreases from 2 to 1, then the substitution effect is given by the change in compensated demand. So the price of the other good Py doesn't change. We want to tie the individual to the same indifference curve, which fixes the utility level at the initial level U bar. And the thing that changes is the price of good X. So the new price is 1 and the old price is 2. So the substitution effect is a change in compensated demand, and the total effect, so the total change in demand for good X, is equal to the difference in the uncompensated demand. So there we have the substitution effect and we have the total effect, and then we can back out the income effect because the total effect is identical to the substitution effect plus the income effect. Now we can solve for the income effect. So the income effect is the total effect minus the substitution effect. Okay, so we now know that the compensated demand function is a very important concept. So the next question is, how can we find an expression for the compensated demand function? Now, one way of finding it is to use Shepard's lemma. So if we know the expenditure function, we can differentiate the expended function with respect to the good of which we want to consider the price change. And if we take the differential with respect to the price, then what we get is the compensated demand. Now the intuition for this is as follows, and maybe it's best if I just will write it on my tablet. So suppose that I currently buy 5 units of ice creams, and that the price of an ice cream increases by, say, 10 cents. How will that change my total expenditure? Well, given that the price in ice cream changes by 10 cents, and I currently buy 5 units of ice cream, my total change in expenditures is equal to 50 cents. So stated differently, if I know that given a small change in price of say 10 cents, my total expenditures change by 50 cents, then I can back out that apparently I bought 5 ice creams, because that leads to that change. So we can rewrite this thing over here, saying that the compensated demand is the change in expenditure divided by the change in price. Of course, this works only for very small price changes, because if the price change is large, then I will also adjust my consumption of ice cream. But for small price changes, the differential of the expenditure function with respect to the price gives you the compensated demand. I can also do a more formal proof. So from the previous lecture, we know that the expenditure function is our solution to the expenditure minimization problem. So here's our objective. We want to attain a utility level U bar. So we need to choose X and Y such that that utility level is reached. And we want to minimize our expenditures in order to accomplish that. And then Shepard's lemma follows from applying the envelope theorem, which you can find in chapter 2 of the book, which says that at the optimum, after we've done the optimization, only the direct impact of a variable on the objective function matters. So we already chose the optimal X and Y, given the prices and given the utility level that we want to obtain. So if then we do a very small change in the price, only the direct impact of the price change will matter, and not that we start to re-optimize. So because the price change is only very small, so we stay with our consumption more or less at the original level. So formally, the total effect of a price change on our expenditures is identical to the partial derivative of the expenditure function with respect to the price of good X, and we at the optimum level. So that one is identical to the partial derivative of the Lagrangian with respect to Px, and that one is equal to the compensated demand. So again, given that I buy 5 ice creams, the price increases by 10 cents. The direct impact is that it will increase my expenditures by 50 cents for these 5 ice creams that I buy. Second order effect is that I might change my optimal consumption of ice creams. I might buy a different number of units, but if the price change is sufficiently small, that indirect effect, that second order effect, is negligible. But the extra expenditures of 50 cents, they are not. Okay, so let's do an example. Let's take an easy Cobb-Douglas function where we take the parameter values alpha and beta equal to 1/2. Then our expenditure function is given by the expression that we have over here. And knowing the expenditure function, we can easily find the compensated demand function for good X by differentiating the expenditure function with respect to Px. So that's an easy thing to do. And we arrive at the following expression. The neat thing now is that given that we have an expression for the compensated demand function, we can easily compute the substitution effect if we change the price of Px, because we can just plug in the different values, the old and the new value of Px. So suppose, for example, that the price of good X increases from 1 to 4, and given that the price of the other good Y, stays put at 1, and that we want to remain, we tie ourselves to the indifference curve associated with a utility of 2, then the substitution effect simply becomes plugging in the new price into the expression for the compensated demand minus the expression for the compensated demand while plugging in the initial price of good X, and we will find that the substitution effect is identical to -1. So because of the price increase, we will reduce our consumption of good X by 1 unit. In addition, life has become more expensive, so there will also be an income effect, and if X is a normal good, that will lead us to reduce our consumption of good X even further. In this example, we consider the effect of a price change that is quite sizable. So we increase the price of good X by 300% from 1 to 4. Next, what we're going to do is to disentangle the total effect into a substitution effect and an income effect when the price change is only marginal. It's very small. And in order to do that, we start out with the definition of the expenditure function. So the expenditure function tells us that given that we want to attain a utility level U bar, and given that the prices of good X and good Y are equal to Px and I, what are the minimal expenditures that we need to make in order to attain that utility level? Now, given that definition, it holds that given the prices and given that we want to reach a utility level U bar, our demand for good X will be equal to the compensated demand if we plug in these values. If we give this individual exactly the income that is needed to reach that utility level, then the Marshallian demand for good X of this individual will be identical to the compensated demand. So we have this equality, and now we can differentiate both the left-hand side and the right-hand side of this equation with respect to Px and rearrange. On the left-hand side, only the first term depends on the price of good X, Px. So on the left-hand side, we have the partial derivative of compensated demand with respect to Px, and the price of good Y and the utility function are both exogenous. They don't respond to changes in the price of good X. On the right-hand side, it's different. So we have 3 terms, and the first term clearly depends on a change in Px. So we have the first partial derivative of X with respect to Px, but then inside we have that the demand function is a function of the expenditure function, and the expenditure function itself also depends on Px. So we apply the chain rule. So we take the partial derivative of X with respect to the expenditure function and multiply it with the derivative of the expenditure function with respect to Px. That gives us the so-called Slutsky equation, and then we rearrange this equation and we solve for the partial derivative of X with respect to Px. And then we get the following. And this tells us that the total effect of a price change in good X on the demand for good X is identical to a substitution effect and an income effect. And then the second term on the right hand side, the one in blue, can be rewritten as follows. So, and then the question, of course, to you is, okay, how can we arrive from this equation over here to the expression over here? So why? Now, a number of elements here. So first, because of Shepard's lemma, we know that the partial derivative of the expenditure function with respect to Px is equal to the compensated demand. So we can substitute this part over here by the compensated demand. Then we can replace the expenditure by income, because income and expenditures, they amount to the same thing in the uncompensated demand function. So that leads us to substitute the E for a capital I here. And finally, at the optimum, it needs to hold that the compensated demand and the uncompensated demand are equal. So if we have an income I that allows us, and given prices P, X, and Y, and we maximize our utility such that it reaches the utility level V, then we, at the optimum, we will consume X units of good X. And given that we want to minimize our expenditures in order to reach exactly the same utility level V, and given exactly the same prices, then we will consume at the optimum level the number of units XC. So we can, instead of XC, we can write X, because at the optimum level they are identical. So that brings us to the famous Slutsky equation, and the Slutsky equation decomposes the total effect into a substitution effect and an income effect. Now, the substitution effect is always non-positive. And why is that the case? Well, as said, we tie the individual to the initial indifference curve, and the individual will always or will never substitute towards the good that has become more expensive. In case of perfect complements, he cannot substitute away from the good that has become more expensive, so he will leave his consumption unchanged. The substitution effect is zero, but in all other cases, the substitution effect will be negative, as the individual substitutes away from the good that has become relatively more expensive. So this thing is negative or zero, and the income effect will depend on the sign of the partial derivative of our consumption with respect to income. So for normal goods, it is positive by definition, and for inferior goods, it is negative. So economists, they like elasticities, and they often use elasticities in order to express how demand responds to price changes. So why this love for elasticities? It is because elasticities do not depend on the unit of measurement. So it gives you the percentage change in quantity demanded given the percentage change in price. And it doesn't matter whether you express the price in euros, in dollars, and it doesn't matter whether you express demand in kilograms or in grams or tons. Now, then the most frequently used elasticities are derived from the uncompensated demand functions. And these are the elasticities that you know well. So we have the own price elasticity of demand, which is derived from the Marshallian demand function. We have the income elasticity of demand, and then we have the cross price elasticity of demand. Question you may have at this point is, okay, do we also have compensated price elasticities that are derived from the compensated demand functions? And the answer is yes. So the compensated own price elasticity of demand is defined as the derivative of the compensated demand with respect to the price of the good that we consider, multiplied by the price of the good and the demand, compensated demand, divided by the compensated demand of the good. And likewise for the compensated cross price elasticity of demand. So these definitions look very similar to the ones that we know, but instead of using the uncompensated demand, it uses the compensated demand. So again, we keep the utility level fixed. And what then are the relationships between the uncompensated and the compensated demand elasticities and price elasticities? Well, we can find out by using the Slutsky equation, because the Slutsky equation relates the uncompensated demand and the compensated demand. So I will again switch to the tablet, where I will repeat the Slutsky equation, and then I will do a number of manipulations in order to derive at the elasticities. So let's do that. So this is the Slutsky equation. And what I will do as a first step is that I will pre-multiply every element by px and divide by x. So on the left-hand side, I will multiply this term by px and divide by x. And I can do so if I also do it for all terms on the right-hand side. So I multiply by px and I divide by x. And also this one, I multiply by px and I divide by x. And then what I will do in a second manipulation is that I will, the second term on the right hand side, I will multiply and divide at the same time by capital I, by income. So this is also manipulation that is okay. So I divide by y and at the same time I multiply by I. So in total nothing happened. It's just multiplying by 1. If you multiply by y and divide by I at the same time. But now we have expressions that are elasticities. So we now have that on the right hand side, if we wrap a number of terms together, so if we wrap together these terms over here, what we have is the uncompensated income elasticity. So this is the definition of the uncompensated income elasticity. And now then we have some terms left here on the right hand side. So that's the part over here. Now for clarity I will repeat. So these are the terms px times x divided by I. And you immediately see that this is identical to the expenditure share of good X. So it's the amount of money that we spend on good X. So we buy X units, we pay a price of Px each. So in total we spend Px times X on good Y, on good X. Our total income is equal to Y. So the share of income that we spend on good X is equal to this number over here. And then, well, the first term on the right hand side, you also recognize this one because that is the percentage change in compensated demand given a change in price of good X. So this is the compensated price elasticity of good X. So this is this one over here. And then on the left hand side we have an expression that is quite familiar because this is the uncompensated price elasticity of good X. So this is the EXPX without the index C. Okay, so now we can return to the slides. So this is what we actually did. We pre-multiplied the equation with px over x. And then the second term on the right hand side we multiplied and divided by I in order to arrive at this expression over here, where Sx is the income or the expenditure share on good X. And now we have a relation between the uncompensated and compensated price elasticities. And now we can get some insights from this. Because now we can answer the question, what is a necessary requirement for a good to be a given good? So we talked about given goods earlier this lecture. And we know that the definition of a given good is that if your income increases, you start to consume less of the given good. So by definition, what makes the good a given good is that the income elasticity of demand should be, or the price elasticity of demand should be positive. If the price of the good increases, we respond by consuming more of the good. So the left-hand side of this equation should be positive. Then the compensated price elasticity is always negative or non-positive. So we derived that on the previous slide. Because we remain on the same indifference curve, we substitute away from the good that becomes more expensive, meaning that if the price of good X increases, we substitute away, we decrease our consumption of good X. And the equality sign here only holds in case good X and good Y are perfect complements. And the consumer has no way of substituting away from the good that has become more expensive. So this part is non-positive. This part needs to be positive. So the only way that will work out is when this thing over here, the final term, is positive. So only then the Slutsky equation can hold. So for a given good, conditions 1 and 2 need to hold, and then automatically it follows that for a given good, this condition here needs to hold. But we know that, well, in order for this term, in order to be positive, the income share of a good can never be negative. So as X always is 0 if we don't spend any money on good X, or positive if we spend the positive sum of money on good X. But it can never be negative. So the only way for this expression to become positive, to undo the minus sign over here, is when this thing is negative as well. Meaning that the income elasticity of good X is negative. So meaning if our income increases, we need to reduce our consumption of good X. So a given good always needs to be an inferior good, because this is the definition of an inferior good. So if this elasticity is negative, okay, then this thing is positive, but it needs to be sufficiently positive, because this expression also needs to be larger than the negative of the compensated price elasticity. Otherwise, these two things together will still be negative. So, and these two terms together will only be positive if this thing is sufficiently large. So this implies that the share of income that we spend on our given good needs to be sufficiently large in order to make this entire right-hand side positive. So practically, it means that items on which you spend only a small fraction of your income can never be a given good. So suppose you have coffee, you don't spend a lot of your income on coffee, so it's not likely that coffee will be a given good, because your income share on coffee is simply too small. So goods that may classify as given goods are goods on which you spend a high share of your income. So energy, food, so basic foods like potatoes, they might be a given good. Okay, so next we turn to compensating variation. So if consumers experience price shocks, then they might want to be compensated, or in order to be as happy as before, to reach the same utility level as before, they need compensation. And price shocks are alive and happening. So inflation in the Netherlands has been relatively low until the start of 2022. But then we saw a sharp increase in inflation, meaning that a lot of goods became a lot more expensive. So there were positive price shocks. And then the question is, how much compensation should one give to consumers in order to make them as well off as before? Translated, to give them the same utility level as before. So how can we develop a monetary measure of the utility gains and also losses that people experience from price shocks? Answer is use the expenditure function, because the expenditure function gives us how much money we need in order to reach a certain utility level. So suppose that the price of a good X increases from P0 to P1, and initially we could reach a utility level U0 when we would spend total expenditures equal to this expression over here. So this is the initial expenditure level that we need in order to reach our initial utility level U0. And now we want to reach that same utility level, but the price of good X has increased to P1. And then the question is, how much extra income do we need to give the individual in order to enable that individual to reach the original utility level? And the answer to that question is given by the construct that we call the compensating variation, being simply the difference between the minimal expenditures needed under the new prices minus the expenditures that we need to make under the old price level. So the difference in expenditures given the change in price of good X, but tying the individual to the same utility level U0. So graphically it looks as follows, and note that in order to draw this picture I have a so-called numeraire good on the y-axis, meaning that the price of good Y is set equal to 1. And I do this because then the difference in expenditures is easily depicted as a vertical distance in this graph. So suppose that initially we faced the price of good X P0. At that original level, this was our budget constraint, which enabled us to reach the utility level U0, depicted by this indifference curve over here. And now the price of good X has increased to P1. So without compensation, the best we can do, given a new budget constraint, is to consume the bundle X2, Y2, and we can only reach an indifference curve associated with the lower utility U1. So how much should we compensate the consumer in order for him or her to reach the old indifference curve U0? Now, that is asking how much do we have to shift the budget constraint outward with the new price ratio, the new slope, up till the point that it just touches on the old indifference curve U0. And well, if we do this in this picture, we know that we have to shift the budget constraint outward to the pink constraint that we've depicted over here. So the slope of this constraint is identical to the slope over here. So it uses the new price ratio, given the new price P1, but it is tangent to the old indifference curve. Now, how far did we move this budget constraint outward? Now, we have a numeraire good on the y-axis. So now suppose that if we would spend all of our income on good Y, and that would enable us to buy 10 units of good Y, it's a numeraire good, so the total expenditures would then be equal to 1 times 10 is 10. Now we've shifted outward. So if now we would spend our compensated income entirely on good Y, then maybe we could afford 18 units of good Y. The price of good Y didn't change, it's still equal to 1, meaning that our new income apparently is identical to 1 times 80. So 18. So the vertical distance here gives us exactly the compensating variation, because it's the difference between the new income level, the compensated income under the new prices, and the income that we had at the original prices, 18 minus 10. So this is the compensating variation. Then there's another construct which is called the equivalent variation, and the equivalent variation answers the question, how much is the consumer willing to give up in order to avoid the price increase? Now, it is clear that the price increase makes the consumer worse off. He can no longer reach the utility level U0, but he can only reach the utility level U1, which is lower. He doesn't like that. He uses utility because of the price increase. And now the question is, okay, how much income do we need to take away from the consumer in order to make him just as worse off as the decrease in utility that he experiences from the price increase? So the equivalent variation says, okay, by how much income do we need to take away from the consumer? So how much do we need to shift the budget constraint inward in order to make the consumer just as worse off as with the price increase? So we shift the budget constraint inward, and we don't change the prices. So the budget constraint stays parallel to the initial budget constraint and the old price ratio, and we shift it inward up till the point that it becomes tangent to the new utility level. And now remember that we have defined good Y as the numeraire good, meaning that the price of good Y is set equal to 1. And this implies that the equivalent variation is shown as the vertical distance between the old income constraint and the new pink income constraint. And this can be seen as follows. Suppose that given our old budget constraint, we would consume only good Y, and we could buy maybe 15 units of good Y. And under the pink budget constraint, if we spend our entire income on good Y, we can buy 10 units of good Y. That is a difference of 5 units, and given that the price of a unit of Y is set equal to 1, it means that the difference in income between the blue budget constraint and the pink budget constraint needs to be identical to 5. So that is the equivalent variation. We need to take away 5 units of income from this individual in order to make him as well off as when he would face the price increase from P0 to P1. And in general, the equivalent variation is different from the compensating variation. So you can see it graphically here. This is the equivalent variation, and the compensating variation shown on the previous slide is larger. So that not necessarily needs to be the case that one compensating variation is larger than the equivalent variation, but they are in this specific case, and in general they are not identical to each other. Okay, so we have the compensated demand curve and we have the compensating variation, and the word compensated is in both of them. Is there a relation between the two? The answer is yes. So in order to see that, go back to the definition of the compensating variation. It tells us the change in expenditure, minimum expenditure needed in order to attain a certain utility level, if the price of good X increases from P0 to P1. So this is like taking an integral. If we have a small change in the price of Px, then our expenditure will also change slightly. That is given by the partial derivative of the expenditure function with respect to Px. And if we make the price change larger, then in order to get a total effect on the expenditures, we need to integrate this expression over the interval from the old price to the new price. And this is done here, and this is the definition of computing the compensating variation. But we know from Shepard's lemma that the partial derivative of the expenditure function with respect to price is identical to the compensated demand function. So we can replace this partial derivative over here by the compensated demand function, and we get the expression over here. But this is very familiar. So we have a function of the price of good X, and we integrate over the interval P0 to P1. So it's not different if you have a function f that's a function of x and you integrate over a certain interval of x. And we hold the price of the other good and the utility constant. Now graphically this integration looks as follows. So this is our function. It's a function of the price px, and because we're economists we always flip the axes. So we have x as a function of px and we put the variable px on the y-axis. And then we integrate over the old price to the new price. And this gives us then the compensating variation. So it's the welfare loss to the consumer caused by a price increase from P0 to P1. And it's identical to this blue area below the compensated demand curve, because that's the function that we use here. Instead of the welfare loss associated with a price increase from P0 to P1, we could also ask the question, okay, what if we take away the opportunity for the consumer at all to buy at a price P0? So we don't increase the price to P1, but we prohibit the consumer to buy good X at all. So compared to the situation where he would be able to buy good X at price P0, the welfare loss will be identical to this entire triangle that runs from A to P0 to P2. So this is the welfare associated with the opportunity to being able to buy at price P0. If you take away that opportunity, you need to compensate the consumer by this entire amount over here. So in other words, the possibility to buy at price P0 is worth the size of the entire triangle, and this is what we call the consumer surplus. So it's the extra benefit that the consumer receives by being able to make market transactions at the prevailing market price, in this case P0. And if you increase the price, okay, then you get a welfare loss, you get a decrease in the consumer surplus. Then an additional question you may have is, okay, we have a compensated demand curve, and we can use that to calculate the welfare loss, but we have fixed the utility level at the initial level U0. But instead we could also use the compensated demand curve plugging in the new utility level U1. And this sounds a little bit arbitrary, whether we take the old utility level as a starting point or the new utility level. So we have two compensated demand curves, and it's not exactly clear whether we should measure the welfare loss with the initial compensated demand curve, with the initial utility level, or with the utility level after the price change. So that makes a difference, because in the first instance we get the area A, B, P0, P1, B, and in the second case we get a much smaller area D, P0, P1, C. And then there's a nice way out, and that is the Marshallian demand function, because we know that this Marshallian demand curve intersects the compensated demand curve and runs below it at the higher prices and above it at the lower prices. So it intersects at point A and point C. And if we take the integral of the uncompensated demand curve over the same price interval P0, P1, we get the area that runs from A, P0, P1 to C. And that area is just in between the earlier areas that we would get if we would use the compensated demand curves. So the Marshallian demand function serves as a good compromise between the two compensated demand curves. If we use that, we get a welfare loss that is just somewhere in the middle of the welfare losses that we would compute if we would use the compensated demand curves. So that's one reason to use the uncompensated demand curve for your welfare loss calculations instead of the compensated curves. And indeed, if you look at the empirical work, then most of the empirical work estimates uncompensated demand curves and uses that to compute the consumer surplus. Now we have reached the end of chapter 5 and we continue with chapter 6. So in chapter 5 we studied the impact of changes in income and changes in the price of the good that we consider. Chapter 6 studies the cross-price effects, so what happens to the demand of one good if the price of another good changes. Now it turns out that we can also have a kind of a Slutsky equation here. So the impact of the change in price of good Y on the demand for good X is the substitution effect minus the income effect. And this expression is quite similar to before. And also if we don't take these very small changes but discrete changes, then the total effect is the change in the uncompensated demand curve. So we just plug in the new price of good Y minus the uncompensated demand given the old price of good Y. That's the total effect. And the substitution effect, again, we turn to the compensated demand curves because we want to tie the individual to the old indifference curve. And we just plug in the new price of good Y. Then we get the compensated demand and we subtract the compensated demand given the old price of good Y. And then the income effect is just the difference between the total effect and the substitution effect. Then there are a number of properties of the cross-price substitution and income effects in the two-good case. So in the two-good case, the cross-price substitution effect must be positive, except when we have perfect complements. And how can that be? Well, if the price of good Y increases, you substitute away from the good that becomes more expensive, in this case good Y. So you substitute towards good X. So a price increase in good Y leads to a substitution towards good X. So that's why the cross-price substitution effect is positive. And if this good X is a normal good, then the cross-price income effect is negative. So we increase the price of good Y, then because of the substitution effect you buy more of good X, but at the same time there's a second effect, your income, your purchasing power decreases, and this income effect leads to you to reduce your consumption of good X. So that holds if good X is a normal good. If it's an inferior good, then the cross-price income effect is positive. And how the net impact of the substitution effect and the income effect combined will be, that is unambiguous. So that depends on your utility function. So some definitions. Two goods are gross substitutes if the partial derivative of the demand curve of demand function with respect to the price of the other good is positive, which means that the positive substitution effect dominates the income effect. So an example might be iPads and Samsung Galaxy, which people seem to consider substitutes. Beer and wine may be another pair of substitutes. If the price of one increases, then the consumption of the other is likely to go up. And we call two goods gross complements if the price increase of one good leads to a decrease in the consumption of the other good. And that means that in this case, the substitution effect is dominated by the negative income effect. So the price of a good Y increases, you substitute away from good Y towards good X, but at the same time your income decreases, and that impact of the income effect is overruling the substitution effect, leading you to consume on aggregate less units of good X. Examples of gross complements might be the iPhone and apps that you use on the iPhone, cars and fuel, etc. And the gross substitutes, they work with the uncompensated demand functions. So, quiz question. We have two goods X and Y, and we know that the derivative of the demand function X with respect to the price of good Y is negative. Which of the following statements must be true? 1. X and Y are gross complements, and 2. X is a normal good. Now, 4 possible answers, and take some time to get to the right answer. Okay, if you paid attention so far in this lecture, then you will have found that answer C is the right answer. If now you are puzzled and you don't know why answer C is the right answer, then maybe you should return to the previous slide, and that contains exactly the answer. But we have a problem with the concept of gross substitutes. So ideally, you want to have symmetry. If one good is a gross substitute of the other good, then the other good should also be a gross substitute of the first good. And it turns out that that doesn't hold automatically. We have an asymmetry. And I will show you with an example. And in this example, the initial price of the two goods, X and Y, is equal to 1. We have a utility function. So it's a quasi-linear utility function, and you can derive yourself that given these prices and given that the income of the consumer is equal to 3, so this is the budget constraint, the red line, price of good X and good Y is equal to 1. So spending all income on good Y gives you 3 units. Spending all of your income on good X gives you 3 units as well. So this is the budget constraint. And given this budget, the highest indifference curve that we can reach is this one, associated with utility of 2. And these green dotted lines give the optimal consumption bundle. In the optimum, we consume 1 unit of Y and 2 units of X. And now we are going to increase the price of good Y. So we increase the price of good Y from 1 to 3. Then we have a new budget constraint. So if we spend our entire income of 3 on good Y only, then we can only buy 1 unit of good Y. If we spend our entire income on good X, then we can still buy 3 units. Given this new budget constraint, the highest indifference curve that we can reach is the blue one over here, associated with a utility of 1. And now consider the cross price effects. So we have increased the price of good Y, and what happened to our consumption of good X? Nothing happened, because in the old case we consumed 2 units, and in the new situation with the higher price of good Y, we also consume 2 units. So the cross price derivative of the price of good Y on the consumption of good X is 0. While at the same time, if we would increase the price of good X, our consumption of good Y would increase. You can check it yourself. So if we would look at that, you would think that good X and good Y are gross substitutes because this thing is positive. But if you take the partial derivative of the demand for good X with respect to the price for good Y, then the value is 0. So they don't seem to be gross substitutes. And that's the asymmetry which makes it complicated. So whether good X and Y are gross substitutes, well, if you look at this one, you would say yes. If you look at this derivative, you would not have no idea. It doesn't seem to be that way. And that's a bit of a nuisance. Fortunately, there is a solution. Instead of gross substitutes, we will apply the concept of net substitutes and net complements. Difference being that instead of using the uncompensated demand function, we will use the compensated demand function. So two goods are net substitutes if a price increase in the one leads to an increase in the compensated demand of the other, and they are net complements if this value is negative. Now, in the two good case, then the two goods need to be net substitutes because your income needs to go somewhere. And if you consider an economy with more than two goods, then it will depend on consumer preferences whether the good will be net substitutes or net complements. But this will guarantee symmetry between the goods, an unambiguous classification into substitutes and complements. Now we talked a lot about income and substitution effects, and the question is, why do we care? At this point, you might be a little bit bored with this entire discussion, so I need to give you a motivation. And the motivation is that the government develops a lot of policies, and many of the policy-related issues, they deal with substitution and income effects. You tax one good, you give a subsidy to a good, that will change the relative price of good, and it will do something to the optimal consumption bundle and also to the purchasing power of people. So for example, suppose that policymakers try to reduce CO2 emissions by levying heavy tax on fuel, then this would have a severe impact on households. So they would be worse off, and the question is, how can they be compensated? Now, as an economist, you would say, okay, driving a car and burning fuel comes with a negative externality to the environment, and this negative externality has to be accounted for in the price of fuel. And one way to do this is to impose a tax. This will cost the household that drive a car money, but you can compensate them by at the same time lowering, for example, the income tax. So that you give them a tax rebate and they are as well off as before. Did nothing change? Well, one thing did change because of the fuel tax. Fuel has become relatively more expensive. Consumers will have substituted away from using fuel. For example, they start to take more often public transport, or they drive less their car but take a bicycle. So the gas consumption has been reduced due to the substitution effect, and consumers are not worse off than before. And these discussions, they occur time and again. So the government wants to do something, they want to fight climate change, so they are going to use the tax tool that they have. Some households will be worse off because of the tax, and how do we need to compensate them? And it's the economist's task to estimate all of these effects and to make proposals about the right and efficient way of compensating households. And it's a political choice to decide to which extent the households need to be compensated. So we conclude this lecture with an empirical paper, and So far, we have assumed that we know people's preferences, we just know their utility function, but in practice, this is often not the case. So utility functions are not visible, and we need to distill people's preferences from their choices, because what people choose in a choice setting, that's the thing that we observe. And people may make consistent choices, and consistent choices are choices that we can represent by means of a utility function, or they can be irrational, and that is when they make choices that we cannot reconcile with a utility function. So what do the choices that people tell us about their underlying preferences? That is the topic of revealed preference. So people reveal the preferences by the choices that they make. So what is the definition of revealed preference or direct revealed preference? So suppose that we have given prices of n different goods, and suppose that given the prices, the consumer chooses a consumption bundle A. So, and the boldface A means a factor. So the bundle consists of A1 units of good 1, A2 units of good 2, and so on till good n. If given the same prices, it would be also possible for this consumer to buy another bundle, bundle B, but he did not do that because we observed this consumer choosing bundle A, then we conclude that bundle A is directly revealed preferred to bundle B. So bundle B can be bought because, well, total expenditures of bundle A are identical to the number of units of good 1 times the price of good 1 plus the number of units that we buy from good 2 times the price of good 2, and so on. So this is the total amount of money that we need to spend in order to buy bundle A. Well, then bundle B is feasible because the total cost of buying bundle B is less or equal than the total amount of money that we need to pay in order to buy bundle A. So given that this is the case, bundle B is not more expensive than bundle A, but still the consumer decides to buy bundle A, then we conclude that the consumer has a preference for bundle A over bundle B. And this is the concept that Andreoni and Miller use in this paper. So what we do here is that now we have a budget line, I1, and the consumer chooses bundle A. So given that this is our budget line, or budget line, and the consumer, given this budget line and given the prices of good X and good Y, he chooses bundle A. Given these prices, he could also have chosen bundle B, but he did not do so. So he directly revealed has a directly revealed preference for bundle A over bundle B. And now what we can do is we can change the relative prices of good X and Y. So now we have confront the consumer with a different budget constraint, I3. So this is the red line over here. Now, notice that given this budget line, it's still feasible for the consumer to buy either bundle A, because that's inside, so it's in his budget set, or bundle B. Actually, given these price levels, buying bundle B will deplete the consumer's entire income. He will have no money left. If instead he would buy bundle A, he can do so. And given the prices, he will also have some money left. So bundle A is really cheaper than bundle B, given the price ratio that leads to budget line I3. A rational consumer then should still prefer bundle A over bundle B, because at the original budget line I1, where bundle A and bundle B were equally expensive, he already preferred bundle A. Now, given the new prices, bundle A is cheaper than bundle B. Now then he definitely should prefer bundle A over bundle B. Any other choice would mean that he is not acting rationally. However, it may be that there are some instances where we will observe that the consumer chooses bundle B. And those are the cases where bundle A is not feasible. So suppose that the budget line of the consumer is I2, then bundle B is feasible to buy. It is on his budget line, but bundle A is not feasible because, well, the slope of this budget line is not that steep, meaning that good Y is relatively more expensive than when the budget line is equal to the red line over here. And bundle A contains relatively a high number of units of Y and not as much units of X. So it means that if the price of good Y is high, then he might afford bundle B, but not be able to afford bundle A. So in that case, we might observe this consumer buying bundle B. Note that we assume in this example that we have strictly convex preferences. So I didn't map the utility functions, I didn't map the indifference curves, but we need to assume that they are strictly convex. So they are not straight lines. So the goods A and B or the goods X and Y are not perfect substitutes. Okay, so what do Andreoni and Miller do in their lab experiment? So they test the axioms of revealed preference. So they allow for indifference curves that are not strictly convex. And the subjects in their study, they play what is called the dictator game. So it's a game where you play in pairs and one player gets assigned the role of dictator. And the dictator needs to decide how to divide a number of tokens. So think of $10 or 10 units between himself and the other subject of the pair. And that other subject has no active role, he's only the receiver. So if the dictator needs to decide how to divide 10 tokens, he might decide, okay, I keep 8 and I give 2 to the receiver. And then the tokens at the end of the experiment, they will represent a certain amount of actual money in dollars. And they implement different treatments. So in one treatment, the tokens have the same value for the dictator as for the other receiver. So meaning if the dictator splits the 10 tokens in, keeping 8 and giving away 10 or 2 to the receiver, the dictator might end up with $8 and the receiver with 2. In a second treatment, the tokens have a higher monetary value for the dictator than for the receiver. So then giving is expensive. So the dictator might think, okay, the receiver also needs some money, some real money at the end. But if I give away one of my tokens, which is valuable to me, it will not give the receiver a lot of money at the end of the experiment. So every token that I give away to the receiver that I don't keep is very expensive. In a third treatment, it's the other way around. There, the tokens represent a lower monetary value to the dictator. So he might not care that much about keeping the tokens or giving it away to the receiver, who can exchange them for a relatively higher sum of money. So they change the price of giving. And if you change the price of something, if you make something cheaper, then usually people should buy more of it. Does it also hold for giving, donating money to others? If it becomes cheaper, do people start donating more money to other people? Now, how do they check this? So they have different subjects and they investigate whether the subjects behave rationally. So whether their choices can be represented by one of the common utility functions. Now, first we consider subject 40 and suppose that the budget constraint of this subject is as follows. So if he keeps all tokens to himself, then he will end up with a payment equal to, I think this is 60. If he would give away all the tokens to the other person, then this receiver would end up with 120 in terms of actual money. So giving here is relatively cheap. And in this case, the subject chooses A. So he chooses consumption bundle A, meaning that he keeps all tokens to himself. Given this, it would also have been possible at a lower price to give away some of the tokens to the other subject, which would give that receiver also some money at a relatively low cost to himself. But he did not do it. He chose the combination A instead of C. So this choice reveals that he prefers bundle A to bundle C. Then the same subject faces a different budget line, one where giving is much more expensive. So keeping all the tokens to himself would give him 120, whereas giving away all of the tokens would give the other subject only 40. So giving here is relatively more expensive. It would have been perfectly feasible for the subject to leave the building with a payment of 60 and none to the other, as with the previous budget line, but instead the authors observed the subject choosing bundle C. So this means we observe the subject choosing bundle C, although he could afford bundle A at a lower price because it's inside the budget set, so some money would be left. So this choice reveals that he strictly prefers bundle C to bundle A. However, in the previous budget line, the same subject indicated that he preferred bundle A to bundle C. So that is inconsistent. So this subject violates the weak axiom of revealed preference. This is how the experiment works. And they do it for many subjects, and they try to classify the different subjects into types. Now, the example I showed you of a subject who violates the axioms of revealed preference, that's the exception. Only 2% of the subjects violate these simple rules. They find that 98% of the subjects adhere to the axioms of revealed preference, and they have some utility function of the form, where the utility function depends on the payoff that you receive yourself, and you care about your own payoff, but you're also altruistic because the payoff to the other person that you don't know because it's an anonymous other player in the lab who you do not meet afterwards, but still your utility depends to some extent on the payoff that the other player receives. And this is showing you that we can easily extend utility functions to include more than the payoff and the own consumption, but we can also incorporate the income or consumption choices of other people. So a first observation that they make is that quite a number of subjects, they make altruistic choices. So they don't keep all the tokens themselves, which leads to the most money to themselves and 0 to the other persons, but they also allocate some tokens to the other people. But people are not all the same, so there are differences between different subjects, and I will show you some examples. So this is subject 38. So if this is the budget line that he faces, he chooses this consumption bundle, which is about an equal split. The amount of tokens that he keeps is such that the actual payoff to himself is identical to the payoff that the other person receives. Then if we make giving more expensive, then he still divides the number of tokens such that both players end up with the same payoff at the end. And if we make giving even more expensive, so you need to give away a lot of tokens to the other in order for that other person to have a decent payoff, then this subject still does it. So this subject really prefers both players to end up with the same amount of money at the end of the experiment. So which type of utility function can describe this type of choices? Question to you. Well, the hint is we make the price of giving, so the good of giving, becomes relatively more expensive. Still, the subject does not substitute away from giving towards self. So apparently there are not a lot of substitution possibilities here for the subject giving his utility function. So apparently he has a utility function where keeping the money and giving it away to the other person are perfect complements. So it's a Leontief utility function, and about 1 out of 7 of the subjects exhibits this type of behavior. Then another subject, this is subject 1. So given that this is the budget line, he chooses this division where the payment to self is 100 and to the other person about 30. If he faces a different budget line, then he changes his choice for the consumption bundle. And if a third budget line, then he chooses this allocation over here. So if we move from the first to the second to the third budget line, then giving to the other person becomes relatively cheaper. So what type of utility function can represent this type of preferences? Well, you give more to the other if the price of doing so is lower. So this is consistent with a situation of perfect substitutes. So if keeping the money gives you the higher a higher payoff, then you keep the money. If it's cheaper to give away the money, then you give away a lot of your tokens to the other person. So you maximize the joint payoff. And about 6% of the subjects, they show this type of behavior. So, and then there is a third one. So this individual, given the budget line 1, he keeps almost all of the tokens, so leading him to or her to receive a lot of money at the end, and the other person not a lot. Then we make giving less expensive. So does the person substitute away from keeping the money towards giving to the other if that becomes cheaper? No, not really. His allocation is still such that he or she will end up with a lot of money herself, and not a lot is given to the other person. And also if we make giving relatively even cheaper, still the person seems to care most about their own payoff, so the dictator in this game. And this is an individual whose preferences can be described as perfectly selfish. So the payoff of the other person doesn't enter the utility function. He maximizes utility, and his utility function is a function of the payoff to self only. Overall conclusion of this study is that we can use our microeconomic models also to model unselfish behavior and also choices that are about giving away money, charitable giving. They can be well described with our common framework, and our utility framework can describe the preference orderings and the choices that people make in those settings reasonably well. That brings us to the end of this lecture. It's been a long lecture, and I hope you enjoyed it, and I will see you the next time, or at least you will see me.